The ironwork stood against the hillside like a cathedral of industry. Stone walls rose 40 feet, blackened by decades of smoke and heat. At its heart sat the blast furnace, a structure of fire brick and iron bands, its stack climbing another 60 feet into the sky. The furnace had been lit for 3 years without pause, consuming charcoal and ore, breathing flame upward through that towering chimney. Men understood the draft. Heat rose. Cold air entered below, drawn through the charging doors and tires by the pull of ascending gases. The stack created suction, reliable as gravity. Fire demanded air, and the chimney provided it without hesitation. This was foundational knowledge, proven every hour by the steady roar of combustion and the predictable flow of molten iron into the casting beds. The furnace drew 20 tons of air each day through its belly. Workers felt the pull when they approached the charging platform. Papers lifted toward the mouth. Dust spiraled upward. The draft was constant, measurable, absolute. It defined the rhythm of the ironworks. Ore went in at the top, air entered from below, and iron emerged at the base. The sequence never varied. The stack itself was a monument to masonry. 4 feet thick at the base, narrowing as it climbed, lined with refractory brick that glowed dull red even on the coldest mornings. Men trusted it completely. The chimney was not a mechanism that could fail. It was stone and mortar, fixed and permanent. Its pull was as certain as the hillside it rested against. On a November afternoon, the furnace master received word that demand had slowed. The blast would be reduced for 10 days while inventory cleared. This was routine. The fire would be dampened, not extinguished. Airflow would decrease but not cease. The stack would continue to draw gently until full operation resumed. Workers closed dampers partway. They reduced the charcoal feed. The roar inside the stack diminished to a low rumble, then to something quieter still. By evening, flame no longer showed at the top. Smoke thinned to a pale thread. The furnace settled into dormancy, radiating stored heat into the November air. Men left the floor, expecting nothing more than the slow cooling of iron and stone. The night shift arrived to silence. The furnace radiated warmth, but the familiar upward pull had ceased. Air near the charging doors hung still. One man placed his hand near the opening and felt nothing, no inward draw, no movement at all. The stack had gone quiet. By midnight, the brickwork had cooled enough to touch without gloves. The internal chamber, which had glowed white-hot 12 hours earlier, now held only residual warmth. Ash lay undisturbed on the hearth floor. The dampers remained partially closed. Everything appeared as it should. Near 2 in the morning, a tender named Boyle approached the lower access door to check the grate. He pulled the iron handle and felt resistance, as though pressure held it shut. When he forced it open, cold air moved past his face, not outward but inward, drawn gently into the furnace. He stood still, uncertain he had felt it correctly. He closed the door and waited, then opened it again. The sensation repeated. A breath of cold November air slipped past him and disappeared into the furnace interior. He pressed his hand flat against the opening. The pull was faint but unmistakable. Air moved toward the ash bed, toward the cooling iron, toward the base of the stack. Boyle called to the night foreman. The 2 men stood together at the door, testing the flow with hands and faces. The movement was gentle, almost tentative, but it was there. The furnace was drawing air inward, just as it always had, except now the fire was dead. The stack no longer pushed heat upward. Yet somehow, air continued to flow into the structure. The foreman said nothing at first. He walked to the opposite side of the furnace, to a second inspection port, and opened it. The same cool inflow greeted him. He moved to the charging platform 15 feet above the floor. There, too, he felt the pull. Every opening into the furnace drew air inward, softly and continuously, as though the entire structure breathed through an invisible lung. Neither man spoke of it beyond necessary observation. They noted the phenomenon in the log and resumed their posts. But unease had entered the floor. The furnace was not supposed to draw air without fire. The principle was simple. Heat rises, cold air follows. Remove the heat, and the draft should stop. Yet here was movement, persistent and wrong, continuing hours after the flames had died. By the second night of shutdown, the reversal had strengthened. The gentle inward pull had become a steady draw. Men standing near the base of the furnace heard a low whistle, air sliding past gaps in the brickwork. Ash on the hearth floor began to lift and scatter toward the center, pulled by the unseen current. One worker wedged a strip of cloth into a crack near the charging door. The fabric stood horizontal, streaming inward, fluttering in the flow. He left it there as proof. Others came to see. The cloth did not waver. Air moved continuously into the furnace, drawn by some force they could not name. The charging platform, 20 feet above the floor, offered a more direct view into the stack. A man named Creighton climbed the iron ladder and stood at the edge, looking down into the throat of the chimney. Normally, heat and smoke would have driven him back. Now he saw only darkness and felt only the cold inward breath. He dropped a handful of sawdust into the opening. Instead of falling straight down, the particles angled toward the center and vanished into the shaft, pulled deeper by the draft. Creighton leaned over the edge, listening. From far below came a sound like wind moving through a cave, low and resonant. The stack was not silent. It hummed with the passage of air, but the direction was reversed. The chimney, that towering column of brick and iron, was exhaling nothing. It was inhaling. He descended and reported what he had seen. The furnace master arrived within the hour, carrying a lantern. He climbed to the charging platform, held the flame near the opening, and watched the tongue of fire bend inward, drawn toward the stack. He extinguished the lantern and stood in darkness, feeling the cold air move past his face in a continuous stream. Below, on the main floor, doors began to rattle. The iron access panels, secured with heavy latches, vibrated against their frames. The sound was rhythmic, almost breathing. Men stopped their work to listen. The furnace had become a presence, no longer passive stone and mortar, but something active, pulling at the air around it with steady insistence. One worker placed his ear against the outer wall. He heard the movement inside, the rush of air through passages and chambers, a sound that should only exist when fire burned. But there was no fire, only cold, descending air and the deep hum of the stack. He stepped back, unwilling to remain in contact with the structure. The day shift gathered around the furnace in the grey morning light. Rumours had spread through the workers' quarters. Some men claimed the brickwork had cracked, allowing air to escape from below and creating a false draft. Others insisted a damper had been left open at the top, allowing wind to force air downward. A few believed the stack itself had failed internally, collapsing just enough to reverse the flow. The furnace master ordered a full inspection. Bricklayers climbed scaffolding to examine the exterior of the stack, searching for cracks or displaced mortar. They found nothing. The chimney stood intact, its surface unbroken, its bands tight against the stone. At the base, men crawled through ash pits and air channels, looking for gaps or collapses. Every passage was clear, every grate in place. Arguments began on the floor. A senior tender named Walsh insisted the dampers had been set incorrectly, trapping cold air inside that now sought to escape downward. The damper operator, a younger man named Pike, produced the logbook showing every valve position, every adjustment made during shutdown. Nothing had been set incorrectly. The furnace had been secured according to procedure. Walsh remained unconvinced. He climbed the stack's external ladder to the top, 60 feet above the floor, and examined the crown. The dampers were visible, partially closed as specified. He opened one fully, expecting the flow to cease. Instead, the sound from below intensified. The inward pull grew stronger. He closed the damper again, confused. Opening the top had not stopped the reversal. If anything, it had increased the draw. A metallurgist from the company's main office arrived by afternoon. He listened to the descriptions, examined the stack, and placed instruments near the openings. He confirmed what the workers already knew. Air flowed steadily inward at every access point. He measured the velocity with a handheld anemometer, 2 feet per second at the lower doors, 4 feet per second at the charging platform. The draft was not subtle. It was measurable and strong. The metallurgist offered no explanation. He suggested waiting for the furnace to cool completely, as though temperature might be involved, though he could not say how. The men on the floor grew frustrated. They had worked with furnaces for decades. They understood fire, heat, and draft. This behavior defied that understanding. A chimney pulled air upward when hot and did nothing when cold. That was the rule. This furnace broke the rule. Blame shifted from person to procedure to structure. The original builders were criticized for poor design. The hillside placement was questioned. Some wondered if underground passages beneath the ironworks allowed air to flow in unexpected ways. None of these theories explained why the reversal had begun only during shutdown, not during years of normal operation. On the fourth day, a pattern emerged that no one had articulated. The inward draft was not constant throughout the day. It strengthened in early morning and weakened by afternoon. At night, it increased again. The rhythm matched the ambient temperature outside the ironworks, though no one had yet made the connection explicit. A mason named Garrett, assigned to monitor the stack, began taking notes. He recorded the temperature of the outer brickwork at different heights. Near the base, the stone was cool to the touch. Halfway up, it retained faint warmth. At the crown, 60 feet above, the brickwork was still noticeably warm, far warmer than the morning air. The stack was cooling unevenly. Garrett descended and reported his findings to the furnace master. The information seemed trivial at first. Of course, the stack cooled unevenly. It was 60 feet of solid masonry, thick enough to hold heat for days. But the master paused, considering the implications. If the top of the chimney remained warm while the base had cooled, the temperature difference might create some effect, though he could not yet name it. He ordered thermometers placed at intervals inside the stack, lowered on chains through the charging platform. The readings confirmed the gradient. The lower chamber was scarcely warmer than outside air. The middle section held residual heat. The upper third of the stack remained significantly warmer, baking outward through the brick. The furnace master stood at the base, looking upward into the darkness of the internal shaft. He tried to visualize the column of air inside, cold at the bottom, warmer at the top. That arrangement was the opposite of normal operation, when fire at the base sent hot gases upward. Now the stack held an inverted temperature structure, cool air resting beneath warm stone. He did not yet understand the consequence, but he sensed relevance. The stack had become a tower of cooling gas, not rising but settling, contracting as it lost heat. Somewhere in that process lay the answer. The furnace was not malfunctioning. It was responding to conditions that normal operation never allowed to develop. That night, the inward draft reached its peak intensity. A door left unlatched on the hearth level slammed shut with enough force to crack its hinge. The sound echoed through the ironworks. Men working nearby stopped and stared at the furnace, its surface dark and cold, yet clearly alive with unseen force. One worker placed his hand over a gap in the access panel and felt the pull against his palm, strong enough to resist his fingers. The furnace wanted air, demanded it, drew it inward with mechanical persistence. He stepped back, unwilling to test the strength further. The stack had become something other than stone. It had become a throat, swallowing the night. Attention fixed on the chimney. The furnace master spent hours studying the stack, walking circles around its base, climbing to the crown and descending again. He began to see it not as a fixed structure, but as an active column, a chamber where gases moved according to forces beyond simple heat and flame. He consulted engineering texts brought from the office library. Most discussed draft in terms of combustion, the upward pull created by rising heat. None addressed what might happen when a furnace cooled. The assumption in every text was that draft simply ceased when fire died. The stack became inert, a passive tube open at both ends. But this stack was not passive. It continued to move air with force and consistency. The master reasoned that if the inward flow was real and measurable, some principle must govern it. He began sketching the situation. A tall vertical column, warm at the top, cool at the bottom, open to atmosphere at both ends. He labeled temperatures, noted the direction of flow, and searched for the mechanism. A foreman named Dietrich, who had worked at foundries in Pennsylvania, offered an observation. He had once seen a mine shaft draw air downward during summer months, when the deep earth remained cooler than the surface. The shaft acted as a passage for cold air to sink, displacing warmer air below. Perhaps the stack was behaving similarly, except the temperature arrangement was reversed. The furnace master considered this. If the upper portion of the stack remained warm while the lower chamber cooled, the air inside would stratify. Warm air would resist descending. Cold air would resist rising. But that did not explain the inward flow. The stack was not moving air between top and bottom. It was pulling air from outside, drawing it inward at the base and charging platforms simultaneously. He climbed to the crown again and held a candle flame near the top opening. The flame bent slightly inward, drawn down into the stack. He dropped a coal through the opening and listened. It struck something far below, the sound echoing upward. The stack was a vertical tunnel, and air moved through it in the wrong direction. Then he noticed the wind. A breeze moved across the top of the chimney, flowing west to east. He watched smoke from a nearby forge stream pass the crown. The wind did not enter the stack, but it passed over the opening, and in doing so, it changed the pressure at the top. He had read about this effect in relation to ship ventilation. Air moving across an opening could create suction. But the inward draft had existed even on still nights, when no wind moved across the crown. Wind might strengthen the effect, but it was not the cause. The answer lay elsewhere, in the cooling gases themselves, in the physics of contraction and pressure. The furnace master was close to understanding, but the final piece remained elusive. On the 8th day of shutdown, a consulting engineer arrived from the state capital. His name was Meredith, and he had studied thermodynamics under European instructors. He listened to the descriptions without interruption, examined the furnace, and requested all temperature readings taken over the previous week. He spread the data across a table in the office and studied the numbers in silence. Then he asked a question: what is the volume of the stack's internal chamber? The furnace master provided the dimensions. Meredith calculated, scratching figures onto paper, pausing to reconsider, then continuing. He set down his pencil and looked up. The explanation, he said, was straightforward once the correct principle was applied. The stack contained a large volume of gas, air mixed with residual combustion products. When the furnace operated, those gases were hot, expanded, and rose continuously, creating the familiar draft. When the fire was extinguished, the gases began to cool, and as they cooled, they contracted. Contraction reduced the volume of gas inside the stack. Reduced volume meant reduced pressure. The interior of the furnace now held air at a pressure lower than the surrounding atmosphere. Nature abhorred that imbalance. Outside air, at normal atmospheric pressure, pushed inward through every opening, seeking to equalize the pressure. The result was reverse draft, air flowing into the furnace rather than out. The process was self-sustaining. Cold outside air entered the furnace, mixed with the cooling gases inside, and was itself cooled by contact with the residual heat in the masonry. That cooling caused further contraction, further pressure reduction, and continued inward flow. The stack acted as a pump, driven not by fire, but by the physics of cooling gases. Meredith explained the role of the chimney's height. A taller stack contained more gas volume, which meant greater contraction when cooled, which created a stronger pressure differential. The 60-foot stack at this ironworks was particularly effective at generating reverse draft. Had the chimney been shorter, the effect would have been weaker, perhaps unnoticeable. He also explained why the reversal strengthened at night and weakened during the day. Cold night, air enhanced the cooling of gases inside the stack, increasing contraction and pressure drop. Warmer afternoon, air reduced the temperature difference, slowing contraction and weakening the inward pull. The furnace responded to ambient conditions with mechanical precision. The furnace master and his men listened in silence. The explanation required no invisible forces, no structural failure, no error in procedure. It was simply thermodynamics applied to a cooling system. The stack had not malfunctioned. It had behaved exactly as physical law dictated, revealing a condition that only emerged when normal operation ceased. Meredith added a final point. The massive masonry of the stack played a crucial role. The brick retained heat for days, creating prolonged temperature gradients that sustain the contraction process. A thinner stack would cool uniformly and quickly, ending the effect within hours. This furnace, built thick and tall against the hillside, had created ideal conditions for extended reverse draft. The engineer's explanation was tested. Workers sealed the base of the furnace completely, closing every access door and blocking every gap with clay. Within 2 hours, the inward draft ceased. The interior pressure equalized with the atmosphere, and the flow stopped. When a single door was reopened, the draft resumed immediately. The test confirmed Meredith's analysis. The physical mechanism was now fully understood. As hot gases inside the stack lost heat to the surrounding masonry and to the outside air, their temperature dropped. Cooler gas occupied less volume than hot gas, a principle demonstrated by every piston engine and steam cylinder. The contraction created a partial vacuum inside the stack, a region of lower pressure. Atmospheric pressure outside the furnace, roughly 14 pounds per square inch, exceeded the pressure inside by a measurable amount. That difference, though perhaps only a fraction of a pound per square inch, was sufficient to drive air inward through any available opening. The larger the opening, the faster the flow. The greater the temperature drop, the stronger the suction. The stack's geometry amplified the effect. Its height created a long column of cooling gas, maximizing the volume of contraction. Its narrow cross-section concentrated the pressure differential, and its thick walls retained heat unevenly, prolonging the cooling process and sustaining the draft over multiple days. Wind across the crown contributed secondary effects. When moving air passed over the top opening, it reduced pressure there through the Bernoulli principle, the same effect that lifts an aircraft wing. This added to the internal vacuum, strengthening the inward pull at the base. On calm nights, the effect diminished, but did not disappear. The primary force remained thermal contraction. The furnace had revealed a characteristic of industrial systems that normal operation concealed. A blast furnace was designed to run continuously, maintaining high temperatures that kept gases expanded and rising. Shutdown was rare, and when it occurred, workers typically sealed the structure quickly, preventing reverse draft from developing. This furnace, shut down gradually and left partially open, had allowed the cooling process to proceed naturally, exposing the hidden behavior. Meredith emphasized that reverse draft was not unique to this furnace. It occurred in any large chimney or stack during cooling, though few were tall enough or thick enough to make the effect noticeable. Mine shafts, ventilation towers, and large flues all exhibited similar behavior under the right conditions. The principle was universal. What made this case remarkable was the scale and the setting. A furnace where workers expected draft to mean only one thing: upward flow driven by fire. The men absorbed the information slowly. Some found it obvious in retrospect. Others remained unsettled, not by the explanation itself, but by the realization that their foundational assumptions about draft had been incomplete. They had believed the stack's behavior was simple and absolute. They now understood it was conditional, dependent on temperature, pressure, and geometry. The furnace had taught them restraint. The ironworks returned the furnace to operation on schedule. Fire was relit, heat built in the hearth, and within hours the familiar upward draft resumed. Gases rose, air entered from below, and the stack roared with normal combustion. The reversal ceased the moment heat exceeded the cooling rate. The chimney once again pulled air upward with the force men trusted. But procedures changed. The furnace master drafted new shutdown protocols. Dampers would be closed fully, not partially. Access doors would be sealed immediately after inspection. The goal was to prevent outside air from entering during the cooling phase, denying the pressure differential the opportunity to develop. If the stack could not draw air inward, reverse draft could not form. Some workers remained uneasy near the furnace during shutdowns, even with the new protocols. They had felt the pull, heard the sound of air rushing inward, seen ash lifted from the floor by unseen force. The memory of that behavior lingered. The furnace was no longer just a tool. It was a system with hidden behaviors, capable of acting against expectation. The consulting engineer departed, leaving his calculations and diagrams. The furnace master kept them in the office, referring to them when training new workers. He used the episode to illustrate a broader point. Industrial systems did not always behave as their primary function suggested. A furnace built to generate heat could, under certain conditions, generate suction. A chimney designed to exhaust smoke could draw air downward. Understanding required looking beyond the obvious, considering forces that only emerged when normal conditions were disrupted. The event became part of the ironworks history, passed from one generation of workers to the next. Men spoke of the days when the furnace breathed backward, when cold air poured into the hearth and the stack hummed with reversed flow. The story carried a lesson. Respect the complexity of iron and stone, fire and pressure. Assumptions were provisional. What seemed absolute could reverse under the right conditions. Years later, as blast furnaces grew taller and more efficient, reverse draft became a known phenomenon, documented in engineering manuals and addressed in design specifications. But at this ironworks, in that November of the mid-19th century, the discovery had been raw and immediate, witnessed by men who trusted their tools and found those tools capable of unexpected behavior. The furnace stood against the hillside, its stack rising into winter sky. Smoke climbed upward, steady and predictable, but the men who worked below no longer took that upward flow for granted. They had seen it reverse. They had felt the force of cooling gases contracting, creating vacuum, drawing air inward with mechanical insistence. They knew now that a chimney was not simply a passage for heat. It was a column governed by pressure, temperature, and the physics of gases in motion. The iron flowed, the fires burned, and the work continued. But the furnace had left its mark, a quiet reminder that industrial systems contained forces both visible and hidden, reliable and strange, simple and profound.